All right. Um, Good morning. We're here to nice talks about the state of side channel attacks, and both of them are quite clever and sophisticated, and basic exploit opportunities in what happens down the OS or the microarchitecture level. I am going to start my talk by showing you that commonly seen real-world side channel vulnerabilities can happen at higher level on the system and can be far less sophisticated. This is what happens for typical application level side channel vulnerabilities. We have a program, it stores some secret information. For the sake of simplicity, let's just assume that the secret information in this case is a 4-digit combination, okay? And we also have the attacker who wants to learn the secret. And if everything is properly secured, the best thing the attacker could do is just to try different combinations. And that obviously doesn't work because that requires exponential number of trials. Now, however, if the program is written in a way such that the secret information is correlated with something the attacker can observe, then the additional observation may greatly help the attacker in reducing the entropy of the secret. For example, if the running time of this particular program is proportional to the common prefix between the secret and what the attacker provided, then the attacker could simply use the timing information as an oracle just to validate his guesses on the prefix of the secret. For example, he could do this for the first digit of the secret and just pick the one that with the longest time. He could repeat this process for each digit and finally reveal the secret. And this will make the attacker reduce the guessing effort from exponential to something that's proportional to k and n. Here, n is the size of the alphabet and k is the length of the secret. Okay? The example here is certainly simple and maybe a little bit silly. And you might wonder, does it really happen in practice? I'd really like to tell you the answer is of course not. But the reality is somewhat a bit more cruel. And this kind of problem happens all the time. Although the application domain described in those attacks are quite different, the core issue is roughly the same. The application developer accidentally correlate the secret with something that's observable by the attacker. And to be fair to the developers, most of those vulnerable code are probably written long ago when side channel vulnerability is not as heavily studied and practiced as they are today. But still, we don't want those code to sit there for decades waiting to be exploited. For that purpose, we built a tool called Themis. Themis is a static analysis that look for side channel vulnerability in Java applications. It takes an input, a Java program, some annotation about the program, as well as a cost model, which I am going to elaborate later. And if it cannot find any side channel vulnerabilities, it is going to give us a proof that this particular program is free of side channels with respect to that particular cost model. Otherwise, it is going to issue a warning telling us something is wrong. Now, of course, we are definitely not the first one to use static analysis techniques on side channel vulnerability detection. There has been some pre-works before, but as always, for any static analysis work, the challenge is going to be to have a nice balance between the scalability of the tool and the precision of the tool. On the one side of the spectrum, we have tools that are based on lightweight static techniques like taint analysis that are known for their good scalability. The problem there is that those tools can be quite imprecise. That means either those tools produces a lot of false positives, or it means that those tools will impose a very strict requirement on how people write code, which will probably reject 99% of the code that we write every day. On the other side of the spectrum, we have the approaches that are based on software verification. Those techniques are known for their good precision. However, they have their own problems. First, sometimes the human has to provide guides to those tools to let them carry out the proof. And second, their scalability is not known as to be good as the approaches that are based on taint analysis. For us, we want scalability, we want precision, we want the ease of automation. And in our tool, we achieve precision by relying on a verifier at the core of the tool. And we achieve automation by replacing the verification algorithm with a custom one that is based on the new logic that we proposed called Quantitative Cartesian Hoare logic, which I am going to refer to as QCHL for the rest of this talk. And we achieve scalability by combining those verifier with a lightweight static analysis. And with the help of all of these techniques, we are able to identify 6 developer-confirmed side channel vulnerabilities in real-world projects like Jetty and Tomcat. In this talk, I am going to expand on each of those contributions, but first of all, I'd like to say something about the definition of this problem. Just this is to give you a formalization of what the example that we have in the beginning of this talk, and as well as nail down the scope of this work. In our model, our definition of side channel vulnerability is based on this classical notion of non-interference, which is what the program analysis community likes to use to describe this problem. In this model, a program is simply something that takes input and produces output. There are two kinds of input the program accepts. One is called high input, which contains secret information that we do not want to reveal to the adversary. And the other ones are called low input, which are things that are not so secret. And for the output, since we're talking about side channel vulnerabilities, we assume the attacker cannot directly observe the content of the output. Instead, the attacker may try to indirectly observe the programs by measuring such as the timing and the energy consumption, the memory traces, etc., and learn something about the secret. Now, if we take this program and we execute it twice by feeding them with the same low input and different high input, we should be able to get two different observations. The reason why a program has a side channel vulnerability is because the attacker can learn something about the high input by relating the difference in observations to the difference of the high input. So if we want the program to be safe, we need the observation to be roughly the same to each other, regardless of how different the high inputs are. So that is the formal definition, and that is what we do. We take a program, and we try to prove that it has this property. If it does not, we issue a warning. Now that we have a definition, let's start by looking into the verifier part of the tool. In our definition, remember, we talk about observations. However, many of the observations, such as the timing or the energy consumption, they are not directly reflected in the program text. So there has to be a way for us to access those informations. And that brings us to one of the probably the biggest assumption that we have in our work is that we assume the existence of a cost model. A cost model is simply something that maps statement in the program into your observation. In this particular example, if the observation is just the timing, then this particular mapping means that if we execute statement one, it is going to take 1 unit of time, and this mapping means statement 2 takes 10 units of time. Now, this is just a very simple, naive cost model. We can definitely extend and generalize it. For example, our cost model could take context other than the current statement being executed and produces different observation according to different contexts. And also, the type of the observation does not have to be a number. It could be a list of addresses representing the memory trace of the program. The point here I want to make is that our approach is agnostic to the cost model. We don't require that the cost model behave in a certain way. All we want is that the cost model give us something for each statement. Okay. And once we have a cost model, the way we incorporate the information into those programs is by taking the program and trying to do program instrumentation. Suppose this particular function is the program that we are trying to analyze, and the parameters of this function is the input of the program. C and K here are marked green, which means that they are low input, and secret there it is red, which means that the high input. Now, if our cost model tells us that every assignment has a cost of 1 and consume 2 are primitive operations that each has the cost of C, then the instrumentation will roughly look like this. We add a new variable cost, which gets initialized to 0, and gets increased by the amount of the cost that each statement takes after the execution of each statement. This instrumentation step basically turns the problem that reasons about observations into a problem that reasons about values in the program variables, which is what those static analysis techniques are good at. Now that we have the instrument in the program, remember the definition of non-interference, we want to run it twice. Now, to make it clear that this is 2 different runs of the same program, I renamed things a little bit to make sure that you know the same variable could have different values. Now, if we have 2 different runs and feed them with the same low input and different high input, then at the end of the day, what we want to check is whether the observations are roughly the same to each other. In this case, we want to check whether the costs are roughly the same. And in our work, to compensate for some imposition coming from the underlying cost model, we don't check for strict equality. What we end up doing is to check for to compute the difference and see if the difference is less than or equal to a predefined epsilon. Okay, so this formalization of the problem is extremely similar to a standard software verification problem, except that the standard verifier would only reason about one program instead of two different executions of the same program. To bridge that gap, the most naive thing one could do is to just merge those two programs and create a new program. And this new program works as if it runs the first execution first and followed by the next execution. Then we essentially reduce the problem of non-interference verification into a standard verification problem. We can just take the program, we take all those assertions, we throw them into the off-the-shelf verifier, and problem solved. However, we tried this first, and we realized that it does not work well in practice. The verifier would reject a large number of programs we throw into it, even though we're pretty sure that those programs are safe. So there's something undesirable going on here with this naive approach. And to give you a high-level idea of what went wrong, here, the assertion basically wants to compare cost 1, cost 2. For most the verifier, or more precisely, the underlying solver, without any guidance, they will try to prove this by trying to infer the value of cost 1 first and then the value of cost 2. And then they try to do the difference, and then they try to prove the assertion. This will be completely okay if the solver is able to infer those costs automatically. However, as we know, automated cost analysis is an extremely hard problem. Even obtaining an asymptotic approximation to those costs is still an open research topic. And to give an idea of how difficult things can get, here is the simple while loop that we had in the early example. And if we compute the cost of this loop manually, this is what we're going to get. And this is going to be a big obstacle for most existing verifier to infer automatically. For example, we have this floor operation here, which means the verifier has to be able to come up with disjunctive loop invariant. And we have this product term here, which means the verifier has to come up with nonlinear invariance, both of which are by no means solved problem in the verification community. So this is the problem. This is hard. We need a way to overcome that. To do that, we propose this quantitative Cartesian Hoare logic. And if we write this logic down, it's going to be a bunch of inference rules. And I know it's early in the morning, and you guys are probably tired from all the travelings you have to do in the past couple of days. So I'm going to do you a favor and put you back to sleep by explaining the meaning of every single Greek symbols here in those rules. Of course, I'm not going to do that. That's not the point that you come here. Instead, I'm going to show you the high-level idea behind our logic. Okay? Here's the key idea. We explicitly acknowledge that cost analysis is a really hard problem, and we consciously avoid doing that as much as possible. This is okay because at the end of the day, non-interference verification does not care about the values of those costs directly. They care about the cost difference. And it is possible to prove something about the difference without knowing all the values. And to see what I mean here, let's go back to our early example. Remember, this is the naive approach where things get concatenated. Instead of doing this, our QCHL verifier would try to do something that is equivalent of merging those two programs in this way, where instead of concatenating the program, now this execution of those programs gets interleaved. Now, in particular, the two loop bodies we see here are merged into one loop body, which means that we are able to simultaneously reason about cost 1, cost 2 while analyzing this while loop. So what does this bring to us? To see what's really going on here, let's zoom in into this while loop and try to figure that out. If we look at this line, we're going to see that each time cost 1 increased by 1, cost 2 is going to be increased by 1 as well. If we look up, this if statement is going to increase cost 1 by C1. This if statement is going to increase cost 2 by C2. And we know that C is a low input, which means that we can assume C1 and C2 are the same thing. Now, this will make us conclude that every iteration of this loop, for every iteration of this while loop, cost 1 and cost 2 will get increased by the same amount. If they are the same thing before the execution of the loop, then it should be easy to conclude that the difference between cost 1 and cost 2 is 0 without thinking about the value of cost 1 and cost 2. Now, if you're looking at the loop invariant required to prove this particular assertion, it's going to be a simple conjunction of a bunch of linear invariants, which means that those kind of invariants are really easy for software verifier to infer automatically. I hope this example gives you some taste of how the verifier works. To recap, what we call is QCHL. It's basically a bunch of tricks to guide the underlying solver away from this hard problem of cost analysis as much as possible. And it does this by trying to interleave the execution of the program and especially fuse those loop bodies whenever possible. Okay, so if you're interested in more details, I'd refer you to the paper where we discuss how do we interleave the execution without explicitly constructing those product program, and also how do we automatically infer those relational loop invariants. Okay, let's move on to the next topic. So far in this talk, the programs that I'm showing you are simple toy examples that looks like this. They are simple, they are small, they're self-contained. But if you look at real-world projects, this will be a more precise picture. They're big and they're messy. And I mean this literally, and this is the call graph that we obtained from the benchmarks that we have in our evaluation. And for this particular benchmark, there are tens of thousands of lines of code and thousands of methods. It would be unrealistic to expect any solver-based verifier to scale to that extent. On the other hand, it probably doesn't make much sense to run the verifier on the entire program because not all the programs handle secret. What really matters to us are the part of the program that actually touches those secrets. And if the project is well written, then those part of the code will be small, will be simple, will be well encapsulated, and the size of those codes will not grow as the size of the entire project grows. And in this particular example, maybe that only a couple methods touches the actual secrets, and in our paper, we call all of them hotspot method. This is where we should focus our efforts on. This is what our verifier should really look at. The authors of this paper were lazy animals. We don't really want to read the source code of all those projects and figure out what are the hotspots manually. Instead, what we did was to come up with a way to automate things a little bit. And the way we try to automate things is by using a lightweight taint analysis. And more precisely, we look for all the fields and variables in the program that look like secret, private keys, password, etc. We mark them all as tainted. And then we perform taint propagation and then find all the method that reads from those taint variables. And after that, we're going to get a bunch of methods that might call each other, but for our purpose, we only want some entry point to the verifier, so we just pick all the methods that are not invoked by any other tainted method and invoke our verifier from there. So if you look at this from another perspective, what we are trying to do here is to achieve a division work where we use a coarse-grained analysis to scan the entire project and nail down what the important piece of code. And then on those code, we run the verifier, and we use a more precise verifier to make sure that we can reduce the number of false positives as much as possible. Okay. And if we put everything together, this is how it's going to look like. You have the program, we have the taint annotation, we send them all to the taint tracker. It's going to do this taint analysis and give us a bunch of hotspots. And then we take the cost model, we instrument the hotspot method according to the cost model, and then we send the result into the verification tool. And this is the part where we're going to get our final result. What we call themis is merely a wrapper around everything in the middle of this graph. Okay. So for evaluation, I'd like to show you 3 set of highlights. The first set of evaluation is in particularly about the verifier part. And for that, we compare with the state of art, which is called Blazor. Blazor is also a tool that tries to prove noninterference. And instead of trying to reason about 2 different executions of the same program, they rely on this very neat trick called decomposition, which only reason about a single program and combined with some cost analysis. And for the micro benchmark they had in their paper, this is the time it takes for Blazor to either verify or reject the program. And this is the time it takes for Themis to either verify or reject the same program. And here, the y-axis is the time, and lower is better. The takeaway point here is that our verifier outperformed state of art with similar precision. Our next set of evaluation is about the effectiveness of the taint analysis. For that, we evaluate our analysis on real-world benchmarks. And this is the size of those benchmarks. And as you can see, some of them can be quite large. And after we run the taint analysis and get all the hotspot method, this is going to be the size of all the methods. Notice that the y-axis is in log scale. So the takeaway point here is that our taint analysis is really effective in reducing the size of the program the verifier has to look at, and therefore it is very crucial and enable us to look at real-world code. And the final set of evaluation is about zero-day vulnerabilities. We run Themis on real-world projects, and we manage to get 7 vulnerability reports. We report them all back to the developer, and the developers confirm 6 of them within 48 hours. Moreover, if the developer later provide a fix to the problem, we can actually take their fix and verify that their fix actually patches the problem. So, in conclusion, we build a static analysis tool called Themis, which is precise, is easy to automate, and has reasonable scalability. We achieve precision by relying on the verifier. We achieve ease of automation by using QCHL, and we achieve scalability by combining the verifier with a scalable lightweight analysis. We believe our technique could be more widely applicable. For example, we could use it in another language, another cost model, or on the other level of the software-hardware stack. Earlier, Mohit asked the question, is there any generalized theme behind all the attacks, behind all those crypto attacks? And I hope that our idea applied on the right level of abstraction might be one of the answer. And with that, I conclude my talk, and happy to take any question. Yes. And that's the place where I'm going to apply the QC. Yes. Yes. I think that piece is really interesting. What are the constraints on the QCS of these? Where it can handle different kind of programs that especially for those type of thing, or where it handle like CCS implementation? Well, yeah. I mean, theoretically, the verifier has some limit on its scalability. But I mean, at the end of the day, if you want to look for vulnerability in the real world, it all depends on how large the code that actually processes those secrets are. And the intuition that we have is that they're usually not that large, even for a large project. I have a secret web page well, if your project is not like written in a way such that every part of the code touches the secret, then I'm not sure if this will work. But if, well, fortunately, most real-world projects that we look at does not look like that. And I think it is only limited. The limiting factor is how complex or how large the secret handling code are. And there's no real constraint on the type of code handling. Well, it depends. There are some, language features that are problematic for any stack analysis. Apart from that, I believe the principle should apply.
Yuval Yarom, University of Adelaide. Thank you for the talk. I wanted to ask, how dependent is the performance of your analysis on the complexity of the assumptions? Because, for example, in Java, you need to include the whole JIT compiler and the hardware architecture below it in your assumptions. So if you scale those, how?
Well, for us, our particular technique is, like I said, is agnostic to the cost model. So that cost model is the piece of assumption that we made about the real world. For Java, I mean, in our code, in our own work, we do not take those JIT compilers and underlying systems into account just to make things simple. But there should be, if you have a more comprehensive cost model describing what the real world will look like, I think the principle still applies. Is that, or do you have any?
We can take it offline.
Okay.
Hello, I'm Raghavendra from Oracle Labs, Australia. Thanks for the talk. How do you exactly get the cost model for these real-world benchmarks, Chetty and?
Well, in our experiments, it's really simple. We just count the number of instructions.
Sorry, count the number of instructions.
Yes, and I have to acknowledge that obtaining a good cost model is itself a really hard problem.
Yeah. So count the number of instructions after the slicing?
Count the number of instructions after the slicing, yes.
Yes, okay. Okay, thanks.
Hey, Daniel Genkin, UPenn UMD. I guess as a follow-up to Yuval's question, how do you account for compiler behavior? We've seen attacks where the code, you read it, the source code, it's completely constant time. Yuval and me spent hard trying to read it, couldn't find anything. And then MSVC compiler did something wrong, and the binary, the final assembly string produced to run it was terribly leaky. Now, when you're looking at Java bytecode, you don't know what the JVM would do, what from you go from the intermediate representation in bytecode to actual assembly running, you don't know what happens there.
Yes.
How do you account for that in the cost model? Because you don't know the logic that would take that bytecode and convert it to assembly.
Well, I guess in that case, the right thing to do is to just to lower the level of abstraction and apply our idea down at the JVM level.
Would it scale? Because after you just put the JVM inside your...
I'm not sure if it's gonna be, if you're gonna do this for the entire JVM. Again, you have to get it the right abstraction level. That's the key. Well, I don't think there's any method that could prove the absence of side channel vulnerability for like real world, that take into account everything. You have to make decisions somehow. And if you have the decision right, then that's where our tool come from. But we agree, like making the right assumptions about real world is hard.
Thank you.
Yes, exactly.
So we're still stuck on this cost model thing, but I want to ask a quick clarifying question about what the model looks like. So is it that the model is a function or that takes in a statement and gives you the cost? Because if you do that, does that mean there's no state in the model? Because you gave the example of cache, where you need to sort of remember what happened before to know whether this.
Unfortunately, we have to assume that the model just take care of that in this piece of work. And of course, it would be interesting to see if we can incorporate more state and into our tool and how scalable that is. But for now, this is just a first attempt. And we just assume that all the complicated cost modeling thing are handed to us by someone who really know how things works.
Okay, thank you.